Hi everyone, we are excited to present our project Distributed Machine Learning Inference for our trajectory predictions and showcase the collective effort of our team. Before we dwell into the details, let me introduce introduce the members of our group. We are four of us: Vizan, Z, Ashish, and myself, Kalyani. Mm, Before we dive into the details of our project, let us next slide. Before we dive into the details of our project, let us take a moment to look at the outline of our presentation. This will give you a clear roadmap of the topics we will be covering, and here is what we have in store for you today. Throughout our presentation, we will elaborate on these topics, providing you with a comprehensive understanding of our work on distributed machine learning inference for trajectory predictions. Next slide. Let's start by addressing the problem statement that motivates our project. As you may know, autonomous vehicles rely on accurate trajectory predictions to make informed decisions about their movements. However, this application poses a unique challenge due to the large input of real-time geo-encoded data. Our goal is to address this challenge and find a solution that enables autonomous vehicles to predict trajectories accurately and efficiently. To do this, we need to maximize the throughput of the model, allowing it to process a higher volume of data and predict more locations per unit time. This indeed results in the high throughput requirement of the model, and this problem has driven our team to develop a distributed machine learning inference framework. By distributing the computational workload, we aim to predict trajectory, enabling autonomous vehicles to navigate safely and accurately. Next slide. When regarding the ML model that we have developed, the model usually requires m plus 1 GRU layers in order to predict the m plus 1th position if the trajectory visits the mth cell. And say that the trajectory visits 19 cells, and then the model must have 20 layers in order to predict the 20th position. We need to have many layers for the distributed computing system to be useful. Say reducing the inference time, enabling the model parallelism, and reducing latency. Then in order to have multiple layers, we need long trajectory, or say the long series of cells as the input to the model. In that case, in order to have the same trajectory represented by more number of cells, we need to decrease the size of the grid so that the same trajectory is represented by more cells, and indeed we will be having a bigger number of cells, say C. Having a large total number of cells, we will ultimately have a huge matrix, because every position of the trajectory is represented by one hot encoded vector full of zeros except the position we are currently at. And if that is the case, then the one hot encoded vector have a size C, which is the number of cells. uh, Next will be explained by Z.
So here, let me introduce you first to two different executions for distributed computing systems that deals with distributed inference. So we can have a model and split the model into partitions, and then the execution will be sequential, meaning device A will take part of this model and execute it, and the output will be then delivered to device B, which will then gonna do the inference for the intermediate output from device A. Or the input itself can be split into two sub-inputs sent to two different devices, and then these two devices will have two outputs, and then the two outputs will later on be combined into having the final output. This kind of model is not gonna be used by us, because we can see in here that convolution layers require a subset for of the input to get part of the output. But in our model, we have sequential layers. Therefore, it is not a suitable architecture. However, for such architectures, what happens is that the input is partitioned like into multiple pieces and fed to different devices. And then these devices will get some outputs that will later on be combined into the final output of the overall model. The architecture that we will be using, however, uses partitioning of the model, meaning we have a model that we will split into, let's say, 3 sub-partitions, and we will put each submodel on one node, and the input to the overall model will be sent to the first node. This first node will do the inference using the submodel it has. Then an intermediate output will be there and will be sent to the next node. Then the next node will do the same, and the intermediate output will be sent to the final node that will later on deliver us the final output of the overall model. It will deliver it to the master node. And the master node has also as a job to inform each of the worker nodes about the next worker IP and obviously about the weights of the submodel it is hosting.
Now I will be elaborating on our key design choices and some of the distributed system challenges that we tackled in our project. So the first one is openness. So openness is about ease of extensibility. So in our project, we used an object-oriented programming style, where our architecture is cleanly modularized into multiple subcomponents, where each Python file in our codebase represents each subcomponent. So for example, we have our master.py file, which represents our master class, and the worker.state.py file, which represents the worker class. So this makes it easier to extend each subcomponent individually. Next. So the next challenge we tackled is concurrency. So to do that, we used a lot of multi-threading, which uses the threading library in the Python library. So for example, we use separate threads each for the transfer of model weights, the model itself, and the data to have maximum concurrency. Furthermore, we also use queues to store inputs and outputs between each compute node so that the threads are non-blocking, or in other words, the process is asynchronous. So for example, let's say if node A wants to transfer data from itself to node B, it does not need to wait for node B to process the data, but rather it can just send the data directly to node B and then continue its own execution. So this allows each node to make progress at any point of time without blocking. Next. Yeah. So the last challenge we tackled is transparency. So transparency is about shielding the user from the underlying implementation details or complexity. So in our project, the data that the user needs to input is the initial model, the input data, and the number of nodes. So all the complexities like partitioning, the node configuration, and the inference itself is done all by the master and worker nodes. Yeah.
Here are the code components that summarize our project. At the master node, the configuration step after partitioning starts a thread, which calls the function transfer models. And in a loop, we create a socket for each of between master and each of the worker nodes. And we first send the weights by calling the function transfer weights, which is at the left side. And we send the weights to each of the, we compress the weights and send to each of the worker nodes. Then the transfer models resumes its execution and uh, uh, sends models and the next node, next worker node address to each of the worker nodes. And so at the worker node, the server function accepts the received data and decompresses it, and the client function predicts, compresses the intermediate inferences, and sends it to the next node using its address. Next.
So here, let me first, before presenting the results, let me introduce you to the different variables that can be seen on this table. The energy consumption in Joule represents the energy that was consumed for the deserialization overhead and the serialization overhead. And this was done by assuming that every bit needs approximately 10 picojoule for it to be compressed or decompressed. And this is based on a paper that will be present in the references. And then The deserialization and serialization overhead basically represent how much time was spent to compress and decompress the data when sending them from one node to another. The network payload represents the amount of data that was transferred over the network. The inference time is how much time was spent only for the inference, and the communication overhead in seconds represent how much did it take time to transfer the data from node A to node B. And the latency is the combination of both overheads.
So in all the architectures, the master to the first node and final node to the master communication are most costly processes, which can be seen from the communication overhead times, which are presented in these tables. As we can see from the throughput graph, when we have two nodes, we are not benefiting much from the distribution of inferences, which is the cause for its low throughput. Although we noticed an increase in throughput at node 3, we start to see a decline due to the increased latency as we increase the number of nodes. However, the sequential model had given us a better throughput because our input to the pipeline system is large and the latency caused due to serialization and deserialization times. We have also validated this decline by plotting the line graph for total network payload divided by total time for each of the architectures. And as we can see from this line graph, the trend follows the same pattern as throughputs, expressing the decline in throughput from node 3 to node 6. And we can also conclude that our model is not suitable for distributed inference as it is associated with huge data inputs that have huge communication costs that are caused due to overheads.
Hello everyone. So in this demonstration, we'll be showing how our framework works. Here we can see that we are using Core Emulator. Let me introduce you to Core. Core is a simulation platform that allows us basically to create different configurations and different number of nodes around our master node, which was what we needed since we needed to search for the best combination of the number of nodes. And in here, inside of each node, we will be running two commands. One of these commands will be activating the worker node. So by going to the fifth node in this case, but it is not named 6, I will first activate the worker node. The worker node here is activated, and I can know that when it tells me that it is waiting for some input using the socket. And next, I will activate this command because it allows me to know the number of data inputting and outputting each node. This payload will later on be used for analysis when presenting our results. Here, the distributed test.py basically takes the data and sends it to the master node. And the master node will, as presented earlier, do the rest of the job. So in here, we will see that the model is being loaded and the data is being loaded. As mentioned earlier, the data is huge, so there's some time taken for the data to be loaded. These print statements allow us to follow up with the overhead. We can see that so far, this was the operation of distributing the weights and distributing the IP address of the next nodes. And after that, we will start by sending the input data and seeing after that how this input data will be computed over every node. So if we go to node N2, we see that inferences are being made, and we also see that we are tracking the different timing that interest us for our analysis at the end of this presentation. And then one by one, these nodes are doing the operations needed. And we can see in here the data input and the data output over every node. Once done, we should expect the throughput to be printed in here. And this throughput is the one that is calculated by measuring the number of inferences and dividing it by the time. As expected, we will not have the exact same result as the one inside of our presentation, but based on our different testing, every time we repeat the testing, we are having the same order of performance between the different configurations. And there are multiple reasons related to that. I think this is out of the scope of this discussion, but I just wanted to mention that. And thank you for listening to our work.
So now we are going to explore the code behind our project, starting with the distributed test file, which will allow us to run inferences for a specified amount of time. First, we need to initialize the emulator worker node IP addresses, then let the master, which in our case is just localhost, know about these emulator nodes. Then we retrieve our model, which is a GRU network with 21 layers in our case, and run the inferences on it for 100 seconds. We mainly use 2 threads, one for starting the 3 stages in our architecture and the other to receive the results and store it in the output queue. As we have talked about it previously, the client, the master node, and the worker nodes communicate with each other using a TCP socket. And here we create that socket to provide a communication mechanism for these nodes. The master process starts by dividing the neural network into multiple partitions, with each partition having multiple layers. Then we call the transfer models function, which creates 2 sockets, which we will be talking about it further. And the transfer models function calls the transfer weights function, which will transfer the weights byte by byte. It compresses them and then sends to each of these worker nodes. Then the model socket is used to send the to encode and send the model and the next worker address in the pipeline to each of the worker node. Then we start 2 threads. The infer thread, which will compress the inputs that we receive from the client, then send it to the first worker node in the pipeline. Then the result server thread waits for the inference, like the last inference from the last worker node in the pipeline, which will be the output. The worker node starts with 4 threads, which we will be talking about it now. One of the thread runs in WSocket function, which will create a socket and call the retrieve weights function, which will retrieve the weights byte by byte, decompresses them, and stores it in the model weights array. And similarly, another thread will run in msocket function, which will receive the model and the next node data from the master, and it also assigns the submodel that we have received with the weights that we have received before. And the server function will wait for the master to send the input data through a socket, decompresses them, and stores it in the input queue. And the last thread runs in client function, which will create a socket, just like all the other threads, takes the input data from the queue or the intermediate inference from the previous worker node, compresses the data, and sends it to the next worker node in the pipeline. And this is how the master, distributed test, and worker node Python files work.
Thank you for listening to this presentation, and we hope you enjoyed the content.